Hello, in this class we are going to look at the optical properties and the impact of nanoscale on optical properties. Through this course, that is the underlying theme that we are investigating, which is to look at what does the nanoscale do to specific properties, and then in that context see if there is some interesting product that you can create out of it, interesting technology that you can create out of it, and in that process utilize this interesting phenomena that you are seeing at the nanoscale. So, in this class we will look at the optical properties. Particularly in this class we will keep the intention would be to get an overview of what these optical properties are, but in particular to understand what is that phenomenon that is happening at at a material level that reflects in the form of an optical property that we observe. And then therefore, when you see a variation in that phenomenon, you can understand that naturally there is going to be a variation in the optical property. So, that is the idea that we will explore through this class. So, our learning objectives are we will first look at how materials interact with light. So, this is I think a very important thing for us to understand what is it that is happening when light interacts with matter, and to some degree we may already be aware of it, but for sake of completeness we will look at it to see how materials interact with light. In particular we will look at the band gap. We normally think of band gap from the perspective of electrical properties. So, here we will look at the band gap from the perspective of optical properties and see what is the effect of the band gap on the optical properties, and so that is the aspect that we would like to focus on. And also we will try to understand that the band gap gives you one part of the story. So, even if you have a material with a certain band gap and therefore you expect a certain type of optical property, is it possible that with the same material with that same band gap you can get actually properties that look somewhat different. So, that is also an idea that we need to explore and understand, so that we get a sense of how we can manipulate the materials to suit our applications. We will finally also look at different band structures that are observed in materials, and therefore, in that context get a sense of what is possible with various materials. So, those are our learning objectives. It will give us some idea of the phenomena of interaction of light with matter and some idea of the internal working of the material and how that impacts the optical property that we are observing. Okay, so we will begin by looking at this idea that a material may have a band structure that looks something like what you are seeing here. That there is a conduction band which is vacant, and you have a full valence band. So, we are looking at a material which does not have any impurity level in it, and so it is an intrinsic semiconductor. So, by definition this means the charge carriers present in this conductor, the number of charge carriers that you have in this material or the density of charge carriers that you have in this material will be a direct function of the temperature and nothing else. So, because there is no other impurity level, you raise the temperature, then you have more of these transitions from the valence band to the conduction band, and you have therefore got more charge carriers. These electrons in the conduction band and holes in the valence band will carry out the conduction process for you. So, related to this is the band gap. So, the material has a band gap Eg, and if you take this material and it interacts with light, so we will say that there is a photon of light that comes in, and then that photon has some energy E, and if it has a frequency nu, then its energy is E equals h nu. This is the equation from Planck, and so you have this energy E equals h nu that comes in, and then if the and then it transfers that energy to some electron. So, that is actually a probabilistic process. So, when you so if there is an electron sitting here, So, when light interacts with matter, it may or may not interact with an electron, okay, because it has to sort of reach the same point as an electron, and so there is some probability associated with it. So, you may have some photons of light that arrive at a material that do not interact with any electron, even though they have some energy that they could transfer to an electron, right. So, there is a probabilistic aspect here. So, in any case within the scope of that probability, we will assume that this photon interacts with this electron and it tries to transfer the energy h nu to that electron. Now, if that energy h nu is less than this band gap, this if it is less than, if h nu is less than the band gap, then you are not able to get this electron to make a transition. It is the band gap is a set of energy levels that are forbidden for the electrons in that material, and therefore, this electron cannot go to that location in the band gap, and therefore, it actually does not interact with that photon. So, it is unable to pick up that energy from the photon, and then the photon just passes on without interaction. So, if h nu is less than Eg, no transition is possible. And so, the photon goes through without interaction. If on the other hand h nu is greater than Eg, so E of that energy of that photon, which is h nu, is greater than that of the band gap, then the transition occurs from the valence band to the conduction band. And of course, so therefore, the threshold value is this Eg equals h nu. Okay, so that is the threshold value. With once you cross that threshold value, the transitions begin to occur, and therefore, the light is able to now enable transitions from the valence band to the conduction band. So, interestingly, this I mean, so it means that you need to have this kind of frequency to enable this transition, and if you do not have this frequency, you will not enable this transition. So, this is a general case of an intrinsic semiconductor. We can now look at a range of possibilities of materials with different kinds of band structure, and using the same idea, try to understand what it is that you are likely to observe. So, if you see here, you have 4 possibilities here. The first 2 we are calling as metallic systems. So, in a metallic system, the band structure is such that either you have 2 bands that are overlapping, in other words, the valence band and the conduction band are overlapping, or you have a partially filled band, in which case you have within the same band you have all these empty levels out here. So, this consists of energy levels that are all available and empty, right. So, now in either case, what happens is, if you take the highest occupied energy level, which is here, if you take the highest occupied energy level here, and the highest occupied energy level that is here, then immediately above it, right above it, so right above it are all energy levels that are vacant and available. Okay, so, even here there are energy levels that are vacant and available. So, and these energy levels are extremely closely spaced. So, we are looking at energy levels that are very closely spaced. So, actually, even though we say it is a band, it is not a continuous band in that sense, it is a discrete set of energy levels, but those discrete set of energy levels are extremely closely spaced, to the extent that for our application purposes they appear continuous. So, that is why we draw it as a band. So, even this band that we see here is actually a series of discrete states which are very close to each other, going all the way across. Okay, so, that is basically the idea that we have. So, now when you take a metallic system and any light falls on it, this idea of E equals so there is no band gap here, right. So, there is no it is sitting in the situation where available energy levels are continuously available above the highest occupied energy level. So, therefore, any energy that is available in a photon coming with any energy, so E equals h nu, any value of nu, any value of the frequency, the energy is sufficient to do a transition from this location to some location above it. So, from here to here or from here to here or from here to here, etc. So, you have a continuous set of energy levels to which these electrons can move, and those continuous set of energy levels begin almost directly above the energy level that which at which the electron is currently situated, and therefore, there is no real restriction on the frequency that the incoming radiation needs to have to enable a transition. So, this is what we will have with respect to metallic systems. Then we also have semiconductor systems that we just saw. You can have typically a semiconductor would be one where the band gap is less than about 2 electron volts, and there of course we have this threshold of h nu should be greater than or equal to Eg for the transition to occur. So, if you have an electron here, it cannot transition to a location here, this is not allowed. On the other hand, it can transition from this location to this location, so this is allowed, right. So, that is why you have a certain range of frequencies that will not interact with that semiconductor, it will not and the interaction here would result in a transition, and since a transition is not possible, that range of frequencies will not be able to interact with that material, and only if you cross a threshold frequency of h nu greater than or equal to Eg, the transitions will begin to occur. Now, the same thing is true with an insulator where the band gap is greater than 2 electron volts. So, the same h nu greater than or equal to Eg is a requirement here. So, similarly, something here cannot transition to a location here, it can whereas something here, an electron here can transition to a location here. So, that is the idea that we have, and so correspondingly when light arrives at this material, only if you have energy greater than the band gap you will have a transition. Now, given this general picture, we need to compare this with what we typically consider as visible light to understand what is it that we can expect with respect to visible light when it interacts with this range of materials, right. So, if you take visible spectrum, the wavelength of the visible spectrum is from about 400 nanometers at the shorter end of the wavelength to about 700 nanometers or 0.7 microns on the larger end of the wavelength spectrum, and the longer wavelengths are appear to our eye as red color, and the shorter wavelengths appear to our eye as violet color, and that is how you get the range of colors. So, about 0.4 microns to about 0.7 microns is what the range is. So, the corresponding band gaps are if you do E equals h nu, you will get for the violet end of the spectrum about 3.1 electron volts, and for the red end of the spectrum 1.8 electron volts. Okay. So, this is typically what we see. So, if you take now if you given this range of energy levels between 1.8 and 3.1 electron volts for visible light, if you now take that radiation and look at its interaction with the possible band structures that we have here, if you consider a metal. So, if you look at a metal in this case either with overlapping bands or with partially filled bands, both at 1.8 electron volts as well as 3.1 electron volts, we have some available some available energy level is present within this material somewhere up there. So, there are some available energy levels there, there are some available energy levels here. So, it does not matter whether you have 1.8 electron volts or you have 3.1 electron volts or any value in between 1.8 and 3.1, you will always have some energy level which can accept an electron which is presently seated at the highest possible energy level when you give it this difference. So, you take this electron here and you give it 1.8, it will probably end up here. If you give it 3.1, it will probably end up here, some such thing. So, the entire spectrum of visible radiation that arrives at a metallic surface can be absorbed by that surface, okay, because there are continuous set of energy levels. This is the reason why metallic surfaces are typically blackish in color, or of that nature, they absorb all light, they are not transparent, at least they are opaque, because all the light that falls on it gets absorbed. It is also true of any other system where you will have a continuous set of energy levels. So, for example, graphite is also black for a similar reason. It is opaque for that same reason, that there are continuous set of energy levels available in it, and that is able to absorb the radiation. So, that is the reason why metallic systems are opaque. Okay. So, now given that idea, now if you look at semiconductors and insulators, let us assume that we have a semiconductor of about 2 electron volts band gap. If you look at this, then a photon arriving at 1.8 electron volts. So, we will say it is at 2 electron volts. So, if you take a 1.8 electron volt photon, it cannot interact with this material, because at 1.8 it does not have sufficient energy to get it past the 2 electron volt band gap. So, this will not interact, whereas once you cross 2 to 3.1, all of these will interact. Okay. So, this material will absorb radiation from 2 electron volts to about 3.1 electron volts, right. So, all of that radiation it will absorb, it will not absorb radiation which is between 1.8 electron volts and 2 electron volts. So, what will happen is wavelengths which are between 1.8 and 2 electron volts will actually go through this material, will not interact with this material, it will go through this material. Other wavelengths will get absorbed by this material. So, now if you look at this material in sort of in a transmission mode, so this light on the other side, you keep the sample in front of you and then you see the light coming through, you only see wavelengths which are in the 1.8 to 2 electron volt region coming through to you. So, that if you see is closer to the red end of the spectrum. So, this material will look somewhat somewhat closer to red in color. Okay. So, so somewhere between orange, red, some such color you will see with this material. On the other hand, if you take an insulator, we say its band gap is greater than 2 electron volts. Let us assume that we have an insulator, for example, 4 electron volts. Let us assume that we have an insulator where the band gap is 4 electron volts. If you take an insulator which has a band gap of 4 electron volts and you now look at the visible spectrum's interaction with it, then the entire visible spectrum from 3.1 electron volt to 1.8 electron volt, the entire visible spectrum will not interact with this sample. Okay. So, if you take an insulator with this kind of a band gap and you keep it in front of you and then you have light shining from the other side which is trying to go through the sample and then reach you, all of the visible light will go through this sample. So, all of visible light will go through. Therefore, if you take a sample with a band gap of 4 electron volts, that sample is now going to be transparent to the visible spectrum. So, insulators which usually have large band gaps are typically transparent to visible radiation. And so, therefore, you can see that based on the band structure you can have an opaque material, you can have a transparent material which is having some color based on what frequencies are going through, what frequencies are not going through, and then you can have another material which is basically completely transparent, and so it looks like a clear glass. So, that is essentially what we can possibly have. Interestingly, I think there is one important point that we must pay attention to here, and that is normally we have this intuitive feel that when something comes with something with certain energy comes and hits a surface, then if the energy is not sufficient, it does not go through that surface. If the energy crosses some threshold, it just about breaks through that surface, and then if the energy is high, it will go right through that surface, right. So, that is our intuitive feel for how some material with some energy interacts with another material on which it is incident. So, our intuition is that more energy means it will go through, less energy means it will not go through, right. So, sort of that is our idea of how it will interact. So, notionally we may think that higher energy photons will go through a material, lower energy photons will get absorbed by the material. That would be our intuitive feel, but in this case that intuitive feel is not correct. You will see here that if the band gap is a certain value, when photons with less energy come to that material, they actually go through because they are unable to do the transition. So, they are not interacting with that material. So, or whatever energy they give, they get back and they continue. So, they do not really go through interact and enable any transition. Whereas photons with higher energy actually enable transition and therefore actually get absorbed. So, this is sort of counterintuitive in that sense. Higher energy photons are getting absorbed, lower energy photons are going through the material as though they are as though the material is transparent to them. The material is transparent to them. So, that is I think a very important point to absorb, because it is very counterintuitive to our thinking process. Okay, so that is this idea of transparent versus opaque, higher energy So, this is with respect to the band gap of that material. So, that is what decides whether something is transparent or opaque, and most importantly this is very counterintuitive. Okay, so, it is very counterintuitive. Normally you would not think this to be the case. So, this is this idea of when something is transparent versus when something is opaque. Now, let us look at something more interesting. Again, we have now sort of got a idea of what is happening when light interacts with matter, but this is not the whole picture. It turns out that we can consider possibilities. This is scientifically what is supposed to happen in the material, but in reality you may actually have a situation where it seems like something should happen, but you are actually seeing something else happen. So, we need to understand what is happening. In particular, if you look at something that is transparent, where the expectation is that the material is supposed to be transparent, you can actually create situations where that material is not transparent. So, just to give you some idea here, let us assume that we have a solid material here, sort of like what you see here, and there are 3 dots, 3 colored dots that are present. That is present on one side of that. You keep this disk in front of those 3 solid dots. Let us say we are using some insulating material which is basically having a large band gap. Assume material has a band gap greater than 4 electron volts. So, let us just assume that this is the case, that we have a material that has a band gap that is greater than 4 electron volts. So, as I said, since the visible spectrum is between 1.8 and 3.1 electron volts, in principle this material should be transparent. Therefore, when you have this situation here, where you have these 3 colored dots and you keep this disk in front of those 3 colored dots, you should actually see those dots. You should be able to see through that material and see those dots. So, that is what our expectation is, and indeed this is what you can get. You can easily get this situation with this kind of a material. At the same time, I can assert that it is possible for me to take the exact same material and do something to it which enables me to create a situation where in fact the material is translucent. Okay. So, in the first case it is opaque, in this in first case it is transparent, and so here case 1 it is transparent, in case 2 I have it as translucent, and I can do something more to that material which makes it opaque. In case 3 it makes it opaque, and when I say do something more, I am not changing the composition in any way. So, composition, chemical composition, crystal structure, all of that are exactly the same. So, I am not changing anything to the composition, I am not changing anything with respect to the crystal structure and so on, and you can get this. And this is actually true. I mean, in fact, you can get, for example, samples of zirconia. Zirconia you can get in, which is actually used sort of like an artificial diamond, so to speak. You can get that in transparent conditions. You can also get that in opaque conditions where let us say the light will not go through, and in fact therefore it is used for bio applications, as we saw in one of our earlier classes. So, you can actually get this range of materials, and how do we reconcile that, as given this given the fact that scientifically we are saying the band gap is 4 electron volts and therefore it should be transparent. And as I said, in these 3 cases I have not changed the band gap, I have not changed the chemical composition, and I have not changed the crystal structure. So, the way we accomplish this and the way it is actually happening in the system, it has got to do with what defects are present in the system. So, if I introduce fine porosity or you introduce grain boundaries. If you introduce fine porosity or you introduce grain boundaries, then you will move from something that is completely transparent to something that is translucent, and then eventually it becomes opaque. The more boundaries that you introduce, the more interfaces that you introduce. A boundary is an interface. Similarly, porosity also is an interface, because it is interface between the material and air, for example. And so porosity also introduces interfaces, grain boundaries also introduce interfaces. So, a single crystal that is defect free meaning it does not have porosity, for example. A single crystal that is defect free will be transparent. If you take a single crystal and introduce porosity in it, or you take the same material and make it a polycrystalline sample with some limited number of grain boundaries in it, you can make the material translucent. So, some defects here, some number of defects. So, in this case we have introduced some level of defects. So, if you introduce limited amount of defects, you make it translucent. If you have large number of defects, then the material which was transparent and then later became translucent can now become opaque. So, this is the way in which we can manipulate the optical properties. You can change the band structure itself, or you can introduce defects without changing the band structure. So, all of these processes will help you change the optical property of the material. So, you can, using these techniques, you can make something go from transparent to opaque, and as you will see, there are ways in which we can manipulate the band structure, and therefore you can even change the color of the material if you desire. So, this is the idea behind the optical properties. Incidentally, it is also useful to know what is our visible spectrum. So, the visible spectrum, as we just discussed, is between 400 nanometers to 700 nanometers, which goes from the violet end of the spectrum to the red end of the spectrum. And so, this is the red end of the spectrum, it showed up here. This is red, and this is the range of band gaps, 1.8 to 3.1 electron volts. If you see the distribution of energy across the spectrum, the intensity across the spectrum, then you will find that if you look at light that arrives on the surface of the earth, 44% of it is in the visible spectrum. So, 44% of it falls in this range, 1.8 to 3.1 electron volts. You have about 3% which is ultraviolet. So, about 3%, so this is 44%. So, 3.1. So, if you have frequency or energy, well, let us go to frequency. Frequency which is or wavelength in this case, because wavelength is what I have given you, lambda which is less than 400 nanometers, then that is 3%. Lambda between 400 and 700, that is your 44%, and lambda that is longer than 700 nanometers. Okay, so that is your 53%. So, 53% of the radiation comes in the infrared, 3% in the ultraviolet, and 44% in the visible spectrum. So, that is your full spectrum. So, in fact, when we talk of optical properties and maybe we are thinking about say using it for a solar cell application or something like that, many times in our mind it is the visible spectrum that sticks in our mind. We keep thinking of the visible light that is falling on us. And it is it's a very important thing to be aware of and to use the visible spectrum, but we should also be aware of the fact that less than half the energy that is coming in as radiation from the sun, which is what we are receiving on earth, less than half that energy is coming in the visible spectrum. So if you take the more than that is coming in the infrared, more than what you see in the visible spectrum, and there is a tiny amount sitting in the ultraviolet range of this spectrum. Therefore, it is interesting to see if you can manipulate, if you can take a material and change its band structure so that it absorbs more and more of this complete spectrum, and therefore you can get more and more energy absorbed from the incoming radiation. And in fact, it is in this context that people look at the nanoscale materials from the perspective of optical properties. They would like to use the kind of flexibility that nanoscale materials give with respect to optical properties to try and capture more and more of this spectrum in a more complete sense, and therefore capture as much of the energy as possible. Okay, so how does this happen? So I mentioned that if you go to the nanoscale, the optical properties can be changed. Basically, we are saying that the band gap can be changed. This is a very important thing to concept to remember. See, when we look for band gap of any material, if you look at literature and you look for a band gap of any material, you will only see one value listed for it. You do not see a range of values. Typically, you look for silicon or germanium or something, you will see one value for the band gap that is listed there. And the reason you see only one value listed there is that the general assumption is that you are looking for what is referred to as the bulk band gap, because for most applications that is what we use. We use what is called the bulk band gap, and therefore you see only one value. But through a lot of scientific study, people have recognized that fact that if you actually go towards the nanoscale, if you start from bulk macrocrystalline material and you move towards microcrystalline, nanocrystalline materials of the same substance, then it turns out that the band gap can actually change, and therefore you will have a different band gap for the same material. In other words, you will have the material showing you a completely different optical property by going to the nanoscale, and that is the whole idea of this nanoscale with respect to optical properties. So what actually happens is that you have when you do this transition, when you have this incoming radiation and you do this transition from valence band to conduction band, this combination of an electron in the conduction band and a hole in the valence band, this combination acts as a pair and it is called an exciton. And many times the exciton is what sort of helps us see something as an optical property, that is it impacts what we perceive as the band gap of that material. This exciton actually behaves somewhat like a hydrogen atom, because you now have one positive charge and one negative charge. Of course, you do not have a proton here, you do not have the mass of a proton here, you only have a positive charge and a negative charge, and it behaves, it has some similarities to a hydrogen atom. And so just like you can have a Bohr radius for a hydrogen atom, there is a Bohr radius for the exciton. So it is called the exciton Bohr radius, and this can actually be a relatively large value relative to the size of a typical atom that we are looking at. And this exciton Bohr radius has it basically means that the exciton needs that much space, or it is in a position to move around in that much space, and if you make the particle smaller than that, then the exciton is getting constrained, and this leads to a change in the what is perceived as the band structure of that material, and it is called confinement. This idea is called confinement and changes the band structure. So what we actually see is that, as I said, you can have a large number of atoms, and in that case what in sort of a grain structure or crystal structure, and that would be something that we would refer to as the bulk material. In that kind of a material, you will see the bulk band gap, which is what you will see typically in the literature. So, this is the typical literature value. So, you go searching for a band gap, this is the value that you will get. If you go to the other extreme, you have individual atoms. So, that is an atom, I mean by definition that is a single atom. So, there you do not have a band gap per se, but you have atomic levels. So, you have specific atomic levels which you can then you can access, when you do let us say X-ray diffraction, when you generate an X-ray, that is what you are doing, you are knocking off an inner shell electron and an outer shell electron from a discrete value falls into the inner shell location, and therefore you have a very specific frequency of radiation being released by that atom, which is in the frequency range of the X-ray spectrum. So, that is the other end of the spectrum. So, you have X-rays at that end of the spectrum, you have the bulk band gap material behaving in the bulk showing you the bulk band gap of that material if you have bulk material. Between these two, if you have a small number of atoms, which is typically what you will see in a nanomaterial. Like I said, in a nanomaterial, if you are looking at average distance between atoms is about average interatomic spacing is approximately 2 angstroms in most materials. So, if you have 10 nanometer particle size, which is very likely in many nanocrystalline samples that you see, the particle size could easily be 10 nanometers. So, 10 nanometers is 100 angstroms, and that means this is about 50 atoms across. So, 50 atoms across is that dimension. So, I mean of course, you can make a spherical particle. So, then you assume say the radius is 50, radius is 25 atoms, and then you can figure out how many atoms are there. So, that is what we will assume for a typical nanomaterial. So, if you are talking of a small number of atoms, so of the order of 50 atoms, 100 atoms, 50 to 100 atoms, something like that, then you are actually in a regime that is between single atoms and the bulk. And what we see, what it is then referred to is that it is referred to as a quantum dot. And how this quantum dot interacts with this electron hole pair is what decides what is going to happen with the band gap of the material. So, in particular, if you have let us say you have two particles, one small one and one large one, okay, and let us say your exciton Bohr radius is this much. Okay, so, this exciton Bohr radius clearly is smaller than the large particle, and therefore, in the large particle you see the band gap of the bulk. On the other hand, here it is larger than the particle, and therefore, the exciton is now getting confined within this particle, and therefore, you see a behavior which is different from that of the bulk, and that is what ends up creating a shift in the band gap. Usually it is a blue shift, which means it is moving towards higher frequencies or lower wavelengths, and so this is what happens, and this is called creating a quantum dot, and with this you can change the optical property of that material, and therefore, you can get the same material with a different band gap, and this is very important technical accomplishment for us, because you can now get a range of materials which have a wide range of band gaps, but the chemical composition is exactly the same, and that is a very useful thing for us to have, because many times in technological situations, if you have dissimilar materials, then you have a situation where you can have corrosion between the materials, you can have mismatch in thermal expansion coefficients and so on. So, if you are trying to make a solar cell out of it and you have dissimilar materials present there, then each material may expand in a different way, the cell may crack, and then you will eventually not have something that is working. But if you want to absorb the entire spectrum, you want to absorb the infrared part of the spectrum, the visible part of the spectrum, as well as the ultraviolet part of the spectrum, then you do need a range of band gaps, so that you can capture this entire spectrum effectively. If you have only one band gap, although technically you can capture most of the energy in this process, you actually end up losing a lot of it. You get very ineffective capture of energy if you have only a single band gap. You are able to capture more of the energy only if you have a range of band gaps, and therefore it is necessary to have a range of band gaps, and it is particularly useful if you can have the same chemical composition and same crystal structure giving you this range of band gaps. And so therefore this nano part of it, nanocrystalline approach to manipulating the band gap or designing the band gap, so to speak, is very effective and useful for us. So without going into much detail here, I just wanted to show you the fact that actually the band gap comes due to an interaction between the Brillouin zones and the allowed energy levels of the free electrons. Actually this part of the discussion is explained in considerable detail in another course, in another NPTEL course. If you are interested, you can if you are interested in understanding this in greater detail on the background of how this diagram comes about, what are all the factors that are taken into account to create this diagram and so on, then you please look up this course on physics of materials. It is an NPTEL course. And there are few classes specifically focused on band gaps and Brillouin zones, and what is a Brillouin zone, what is this E versus K diagram that is shown here, and how you can draw this diagram and how these band structures are drawn. So that is a much more detailed discussion there. So I will not redo the discussion here. We will simply use this final diagram that comes from there just to understand the fact that there is an E versus K diagram, and in that diagram there are features, and those features get reflected in the band structure that we tend to draw. Okay, so this band structure that we tend to draw are direct result of where the Fermi energy level is, which is this EF, and how this diagram ends up being. And this is something that is very useful to know. So you please look up this information if it is of interest to you. For our discussion, we will simply take this diagram, and we will keep in mind the fact that this has come because of an E versus K parabola that is possible, and how that parabola interacts with Brillouin zones. So you have these Brillouin zones that, so this Brillouin zones are coming from the crystal structure of that material, and at the boundaries of those Brillouin zones these parabolas distort, and that is how this diagram has come about. So that is the distortion, and these are all the Brillouin zone boundaries that you can see. So those boundaries occur at if you call this 0, minus pi by a, minus 2 pi by a, this is pi by a and 2 pi by a, where a is the lattice parameter. So this is just a quick look at how that diagram comes about. This parabola is the free electron parabola. Okay, so this is all I am going to point out here. There is a free electron parabola. How it interacts with Brillouin zones gives you these distortions of this free electron energy levels, and that distortion is what creates a forbidden energy level here and an allowed energy level. Forbidden, this is forbidden, and this part is allowed, and that is why if you see here you get an allowed energy level in this range. This is allowed and this is forbidden. So that is how you get this bands and band structure. So that is an information that you can look up in this physics of materials course. For our discussion, again with respect to the optical properties, it is also of interest to know that there is something called an indirect bandgap semiconductor, and there is something called a direct bandgap semiconductor. Okay, so direct bandgap semiconductor is there and indirect bandgap semiconductor is there. The primary idea here is that because again we are looking at this from the perspective of optical properties, it is valuable to know whether it is direct or indirect, and the primary difference between them is the location of these positions, which, so this position here. So, for example, here this is the highest position of electron energy levels in the valence band. This is the position of the next available energy level, which is the lowest energy level in the conduction band. And in this diagram on your left here, so this the diagram that I have marked on, those two locations are in the same region in K space, whereas here you have the highest occupied energy level at one location and the lowest unoccupied energy level in another location in another direction, in the B direction. So, you have pi by B and pi by A, and so these are two different crystallographic directions. I mean, because it is a compact diagram, you are seeing it like this, but what it basically means that is that you will have a pi by A position coming in one direction and the pi by B position appearing in another direction, maybe orthogonal direction, you will have the pi by B kind of direction appearing. And therefore, when you do a transition in an indirect bandgap semiconductor, you cannot just go up in energy to get the electron to the next available energy state. So, what you normally have is, if it were a direct bandgap semiconductor, your electron would go straight from here to here if you put energy into it. But in an indirect bandgap semiconductor, you actually have to raise the energy level of the electron, and then you have to also move it to another location in the crystal structure for it to get actually absorbed into the conduction band. And so, from the perspective of optical properties, the direct bandgap semiconductor is much more effective in absorbing the radiation, incoming radiation, efficient. The indirect bandgap semiconductor is inefficient. Is less efficient. So, this is useful to know because it helps us narrow down the systems, the material systems that we would like to focus our efforts on. So, if the material system we pick is an indirect bandgap semiconductor, ahead of time we know that it is not going to be very efficient in gathering photons, because the photons have to raise the energy of the electrons and one more process has to happen before the electron goes to the correct location where it can get absorbed. On the other hand, if you take a direct bandgap semiconductor, if the photon has enough energy to just raise it to the available location where the next available energy level is, then that is all is required, it will get absorbed. So, therefore, the systems that we pick, we would prefer to pick something that is a direct bandgap semiconductor. This is what we would prefer to pick. This, on the other hand, we would not prefer to pick unless there is some other commercial reason why we would need to pick that. So, for example, silicon is actually used quite a bit for solar cell applications, but in fact if you look at it, it is an indirect bandgap semiconductor. It is not a very appropriate material to use, but simply because it is available commercially in large quantities and in a sense relatively cheaper. It is not that cheap, it is relatively cheaper, and therefore people end up working with that. Okay, so the summary for what we have discussed today is that materials of course have optical properties. We are very familiar with materials, with the optical properties that materials display. In particular, we understand that materials can be transparent, they can be translucent, or they can be opaque. So, all these possibilities are there. The band gap of the material has a very significant impact on the optical properties displayed by the material. So, band gap has a very significant impact on the optical properties that the material is displaying, but that is not the whole story. As I said, the band gap plus the defect structure. So, band gap plus defect structure is, so you have to add band gap plus defect structure. So, together they impact the optical properties quite a bit, and the band structure can further be manipulated whether you are in macro size or in nano size, and based on that size you will have a size related impact on the band gap of the material and therefore on the optical properties. So, in reality the full picture is the band gap plus the defect structure plus the crystal size. All three of these together will get us the overall picture that we are interested in of the optical property of that material, and therefore if you take this full combination, you can take one single material system and create a wide range of materials out of it, which show a wide range of different optical properties in terms of the color of that is being displayed, in terms of whether it is transparent, translucent or opaque. So, a pretty complex range of optical properties or a significant range of optical properties can be displayed by the same material if you simply manipulate these things, and we have seen some ways in which this can be done. We also noted that the band structure itself could be direct or indirect based on the E versus K diagram, and as I said there is another course which deals with these diagrams in much greater detail. You can look that up if that is something that is valuable to you. So, the band structure could be direct or indirect, and that again impacts how effectively we see the optical property. So, the optical property you can make a prediction that it is going to do certain things optically. This whether it is direct or indirect tells us how efficiently it will do that display that property. Will it be very efficiently doing it, or it will be relatively inefficiently doing it. So, these three are major conclusions here, that they can have different properties, the band gap can have an impact, and band structure including whether it is direct, indirect and any other defect structure that is present gives us the overall picture of the optical properties. So, with this background we will look at more the nanoscale in terms of how you can create nanoscale materials for optical studies, and what kind of properties you might get from them, what kind of technique you would need to use to probe those properties and examine the result that you get. So, those we will do in our subsequent classes. This is our background for those classes. Thank you.